Okay, this is me going over the homework on this normal distribution worksheet. Right, the first thing to understand about a normal distribution is that a normal a normal distribution means that your data is, if we made a histogram out of it, it would have the highest point in the middle, which represents the mean. And as you go away from the mean, it would each rectangle would go down kind of evenly on both sides. And we're going to call this, sorry, when you draw a curve like is shown in this picture here, that's not a histogram, right? Histograms aren't this smooth curve, they're a bunch of blocky rectangles. So this is an approximation for that. But it's actually, a real world mathematical approximation for situations that tend to be normally distributed. And actually, there's a lot of them out there, right? It's pretty much like everywhere you look, you find normally distributed data. So, first of all, anytime you're doing a problem like this, you're probably going to draw yourself a bell curve to help you understand what it is you're trying to do. And a lot of the questions that you have to answer can be answered by just knowing this information right here, right? So if you look at the bell curve in the middle, that's the mean. Okay, if you count off in three equal parts to the right and to the left, right? 1, 2, 3. Those are going to be the standard deviations um, from the mean. Plus 1, plus 2, plus 3. And same thing to the left. These should be equally spaced, right? Well, we would expect 68% of the data is in between -1 and +1 standard deviations. Okay, but this is a symmetric shape, means it's the same on the left as it is on the right. So we can actually divide this 68% up into 34% and 34%. Okay, and between -2 and +2, 95%. And if you do the math, 95 minus 68 divided by 2, you get this 13.5%. 13.5%. And same thing, 99.7% of the data is in between -3 standard deviations and +3 standard deviations. Right? It's not everything. It's lacking 0.3%, but it's almost everything under the curve is between 3 standard deviations of the mean. So most of the questions not most, but a good part of the questions that we have to answer, you could answer just by knowing that much information. So let's look at our first problem. It says the mean life of a tire is 30,000 kilometers and the standard deviation is 2,000 kilometers. So 68% of the data, right, would have a life between, and I mean, just to show that it should usually be that you're going to draw yourself a curve. First, you draw yourself an x-axis, then you draw yourself a nice bell-shaped curve. You put the mean in the middle. In this case, it's 30,000, which I'm going to abbreviate as 30K. And you knock 3 evenly spaced intervals to the right and to the left. And they said that the standard deviation was 2,000. So I'll just say 32K, 34K, 36K. And to the other side, again, equally spaced, 28K, 26K, 24K. Okay, this said, what percent of the data is in between, or said 68% of the data will have a life between, okay, where did that 68% come from? Well, it came from here, within 1 standard deviation of the mean, right? So, within 1 standard deviation of the mean here would be between 28K and 32K. So I actually did not print out this worksheet, but you're going to fill this in. You're going to say this is 28K to 32K. 95% of the data should have a life between Okay, the 95% is within 2 standard deviations of the mean. For our picture, that would be between 26K and 34K, right? In between these two, that's 2 standard deviations. And then the last, what percent of the tires will have a life that exceeds 26,000? Okay, let's see. 26,000 is here. And we know that the mean is here. There's 50% of the data is to the right of the mean. And then from our picture, what do we expect? In these two segments here, we expect 13.5 and 34%. So this is 13.5 and 34%. So if you add up all of those, you're going to get 50 plus 34 is 84, plus 13.5, it's going to give us 97.5%. So this is again, what do we say? 1A should have been 28K to 32K. 1B should have been 26K to 34K. 1C, which we just did here, should be 13.5 plus 34 plus 50, which is 97.5. D, if a company purchased 2,000 tires, how many tires would you expect to last more than 28,000 kilometers? Okay, so when they ask you how many, that's not a percent question, but you need to find the percent first. So what percent of the tires are going to last more than 28,000? Okay, well, let's see. Go back to our graph. More than 28,000 means from here to the right. So that's 34 plus 50 is 84% of the tires will last more than that. But they didn't ask that. They said, how many out of 2,000? So you're going to have to do 0.84 times 2,000. Right? And what is that going to be? 168. So 1680. You could use Desmos or a calculator to figure that one out. 2. The shelf life of a particular dairy product is normally distributed with a mean of 12 and a standard deviation of 3. Okay, let's draw a picture. This was number 1. Number 2. 12 and 3. So again, you start by drawing yourself a picture. Make yourself a nice bell curve. The mean is 12. The standard deviation is 3. So I should add 3 plus 3 plus 3 plus 3. Go the other direction. That'll be 9, 6, and 3. Okay, that's our starting point. Now we try to answer questions. About what percent of the products last between 9 and 15 days? Okay, but 2A. Between 9 and 15 is like plus and minus 1 standard deviation, that's 68%. 2B. Oops. Right? So again, in between 1 standard deviation to the left and to the right, that's 68%. Next question. About what percent of the products last between 12 and 15 days? Okay. Between 12 and 15, well, that would be half of what we just answered, right? 9 to 15 was 68, so B should be 34%. C. About what percent of the products last 6 days or less? So 6 days or less means to this side, That means to the left of 2 standard deviations. See, um, we know that this is, we actually did all this math up here, where we actually found the area to the right of 2 standard deviations. And what did we get? 97.5%. So what percent is going to be to the left of 2 standard deviations? 2.5%. So you have to understand, what areas are you adding up when you do that, right? You're adding up this area here, which by our graphic, by this, we know that's 2.35%, but they're not telling you what the area is to the left of 3 standard deviations to the left. But this area goes on forever, forever. But if we're going to use these two numbers, 34 and 13.5%, to represent those two parts of to the left of the middle, then what goes to the left of here has to be 2.5%. That's what it's adding up. So we're going to just say C is 2.5%. D, about what percent of the products last 15 or more days? 15 or more, right? So that would go from here and to the right of that. Well, we know that to the right of the middle is 50%, right? This is 50%. But this piece right here is 34%. So what's to the right of that should be 50 minus 34, which is 16%. Three. Sorry. Tres. Lineup for tickets to a local concert had an average mean waiting time of 20 minutes with a standard deviation of 4 minutes. Okay, so I'm going to draw my picture first. 20 and 4. This is number 3. Again, I'm drawing a picture. You should always draw a picture. I'm going to do it over here. It doesn't have to be a perfect bell curve. In fact, it could be quite horrible. As long as it looks like it's unimodal and symmetric, you'll be okay. And I already forgot this. 20 and 4. So 20 is in the middle. The standard deviation is 4. So that's me just labeling that, okay? Let's see, did 3 have multiple parts? Yeah, A. What percentage of the people in line waited for more than 25 minutes? Let's go to our picture. So 25 would be like right there. So what they're asking for is what's the area to the right of that? Well, you can't answer that by counting whole numbers of standard deviations from the mean and using 68, 95, 99.7. So this is where you'd have to use either a table of values or probably in this case you're going to use Desmos. So let's remember how we use Desmos to do normal calculations, right? So let me bring Desmos up. I think I have it open amongst my many tabs here. Obviously, we're going to be going on the left side of the screen. We got to go to the keyboard functions, and this is under DIST for distributions. So normal distribution is this one right here. Click. Now, what the normal distribution is looking for in the parentheses here is the mean and standard deviation. So we had 20 and 4, right, separated by a comma. And then this is what we want to do. We want to find the area under the curve. Now, you might be looking at this saying, that doesn't look good. Let's try to zoom to our data. Oh, that looks a lot better. Okay. Um, Remember, we're trying to find the area which starts at 25. It starts here and it goes to the right, and it never stops going to the right. So what do we need to put in here? 25 is the left side of this interval, so we say 25. And then notice that um, this thing here has kept an infinity symbol. That's just fine. So this is actually the probability. It's 0.0156. If we were going to turn that into a percent, we'd call that 10 point. And how about if we round it to the first decimal place? 10.6%. So 1A is 10.6%. B. If 2,000 ticket buyers were in line, how many of them would expect to wait less than 15 minutes? Back to our graph. 15 would have been here. So if I want to know the percent of them that waited less than 15 minutes, I'm going to need the normal calculation. But then I have to multiply times 2,000 because it asks for how many out of 2,000. So back to Desmos. All right, this time the area we're interested in goes infinitely to the left, right? And then it stops at 15. And let's see if it's going to let us do this. This definitely we're going to replace with a 15. And there you go. You can type the word infinity and it'll bring that up. Okay, so that says this area, which actually doesn't end to the left, goes to negative infinity. If I count up the area under the curve all the way up to, 15, that I get that, right? 10.5%. Now, I need to multiply that. It's actually 10.6. It's actually the same number as this was, but 0.106, 0.106 times 2,000. That's probably something we want to do in Desmos anyways. And we get 212. Okay, that was 3. 4. In an Oreo factory, the mean mass of a cookie is given as 40 grams. For quality control, the standard deviation is 2 grams. Okay, so again, number 4, we're going to draw our curve. For 40 and 2. So this is 40. 1, 2, 3. 1, 2, 3. 42, 44, 46, 38, 36, 34. Answer question. If 10,000 cookies are produced, how many are within 2 grams of the mean? Okay. Well, within 2 grams of the mean means from 38 to 42, which means 1 standard deviation of the mean. We know that's 68%. So this is going to be 0.68 times 10,000. Right? 0.68 times 10,000, which should be 6,800. B. cookies are rejected if they weigh more than 44 or less than 36. How many would you expect to be rejected in a sample of 10,000 cookies? Let's go back to this. So they're asking us for the percent that is not between two standard deviations to the left and two standard deviations to the right. Okay, but what's the area between two standard deviations to the left and to the right? 95%. So what does that leave that's not in between those two? 5%, right? If 95% is between two standard deviations of the mean, then 5% is not. So we can say that's 0.05 times 10,000. And let's see, what should that be? 50? 5%. 10%, no, 500, right? 500. Okay, 5. The speeds of cars on the highway have a mean of 95 and a standard deviation of 5. Okay, draw a curve. See how boring this gets? Okay, and what did this say again? 95 and 5, right? 95 and 5. 95, 1, 2, 3. 1, 2, 3. So this is 100, 105, 110, 90, 85, 80. So I've drawn and labeled my curve before I even read the rest of the problem. What percentage of the cars average less than 85 kilometers per hour? Okay, less than 85 means it's there, right? And that's a whole number of standard deviations from the mean. Again, we kind of just did it up here. If you know that there's 95% of the data in between two standard deviations, then there's 5% of the data that's in these two parts. And that means 2.5%. Half of that is here. A, 2.5%. Okay, that's a question that's intended to be answered by using this rule, the empirical rule, 68, 95, 99.7. But could you have used Desmos to figure that out? Yes. You would have not gotten exactly the same answer, but you would have had close. And in fact, the right answer is what you get in Desmos. B. If police cars stopped cars that were going more than 105, how many would they stop if there were 8,000 cars on the highway? So more than 105 puts us there, which again is just outside of two standard deviations. We know that that's 0.025 for 2.5% times 8,000. Okay, let's do that in Desmos. $200. 6. A bottle of fruit punch contains at least 473 milliliters. The machine that fills the bottles is set so that the mean volume is 477. The volumes in the bottles are normally distributed. Okay, what percentage of the bottles are underfilled if the standard deviation is 2 milliliters? Okay, so we're going to have to answer after we take into account 6 and what it says under the A. Okay, so for 6A, the mean is 477. On letter A, it says the standard deviation is 2, so that makes this is 475 and 473. They want to know what percent are going to be underfilled if the standard deviation, well, 473 is the definition of underfilled according to the problem. So they're asking for what's the percentage to the left of that. Again, just outside of 2 standard deviations from the mean, that's 2.5%. How about B? Oh, you can't see that. Sorry. So here was the 6A. Since it was the standard deviation was 2, I labeled this 477, 475, 473. We wanted the area to the left of that, 2.5%. B, right? Still have a mean of 477, but this time the standard deviation is 4. So that means 473 is actually 1 standard deviation away. And we've done this math before, and that should be 16%, right? Another way to look at it is it's 50% minus 34, which is 16%. 7. A grading scale is set up for 1,000 students' test scores. It is assumed that the scores are normally distributed with a mean of 75 and a standard deviation of 15. How many students will have scores between 45 and 75? So let's see. Draw our curve first. This is number 7. I'm going to draw it over here. So 75, I got to go 1, 2, 3, 1, 2, 3. Right? And the question pertains to the left side of that. So between 45 and 75. So let me just label the less. This would be 60. This is 45. So they're asking for the area in between those two. And we've seen this broken down. Even here, right? That means you're adding up these two. What percent? Add these two up. And that'll be 34, 47.5%. B. If 60 is the lowest passing score, oh, actually, I made a mistake. On A, it said how many students out of 1,000. So I have to multiply my percent. Which is 0.475 times, that was 1,000, right? 1,000. Which should be 475. And B, if 60 is the lowest passing scores, how many students are expected to pass the test? So 60 is 1 standard deviation to the left. So basically we're adding up the 50%, which is the right side, to the 34% here. That makes 84%. And you have to multiply 0.84 times 1,000 equals 840. 8. Oh, I'm already there. But I didn't show that, I guess. So 84%, 80.84 times 1,000 is 840. Done. 8. I hope this is the last one, because this is going on kind of long. It is. Okay, the monthly income of 5,000 workers at the Microsoft plant are distributed normally. Suppose the mean income is 1,250 and the standard deviation is 250. Okay, so draw our curve. One 250, standard deviation is 250, so that's 1,500. 1,750 and 2,000. And this is 1,000, 750, and 500. And there's 5,000 workers. Okay, we need to know that. How many workers earn more than 1,500 per month? Okay, just to do this differently, this is one that you can see by the numbers they use could all be done just knowing the standard percentages. But let's use Desmos instead to do this. How many workers earn more than 1,500 a month? So go to Desmos. The mean was 1250. The standard deviation was 250. We want to find cumulative distributions more than 1,500. So that means, actually I should zoom in. More than 1,500 means it starts at 1,500 and it goes to infinity. Notice the scale, right? From here to here. What percent is that? It's 0.1586, okay? Well, we need to, I wonder if it'll let me do this, times 5,000? No. So 0.159 times 5,000, 795. B, how many workers earn less than 750? Okay, so that means 750 and to the left. So let's do this. All right. Negative infinity to 750. That gives us the percent. It looks like 2.275%. But we need to multiply the decimal form of that. 0.0228. So 114. C. What percentage of the workers earn between 750 and 1,500? Right? Between 750 and 1,500. And there it is, 0.818. I'm going to call that 81.9%. Right, so I'm just writing it in here. Yeah, I'm not doing any of the shading because we're getting it on Desmos anyways. But again, usually like if you want to answer a question like that, between 750 and 1500, like on here, you would like show between those two numbers and then shade it in, right? Show it on here. In between those two numbers, shade in, and that's what you're going for. D. What percentage of the workers earn less than $1,750? Okay, Desmos time. Less than 700, actually 1750. And it looks like you don't actually have to put anything in there. When it's blank, it just assumes it goes on forever. Um, so it looks like 0.9972, so 97.7%. Okay, that was the whole worksheet. Now I want to go back quickly and check our answers. Because there used to be a mistake in one of these, and I just want to make sure we get it right. These all look good. 28K to 32K, 26K to 34, 97.5, and 1680. 2. 6834, 2.5, 16. That looks good. I think it was either on 3 or 4. 3, 10.6, and 2. I said 212, they said 211. That's probably just because the way we had to round this one off a little bit. I wouldn't worry about that. Those kinds of little differences happen in this kind of stuff. Let's see, the next one should have been 6,800 and 500. That was correct. The next was 2.5% and 200. That was correct. The number 6 should have been 2.5% and 16%. So actually, I think these were fixed. Whatever I thought I had wrong, I think I fixed it somewhere. 7, 47.5%. Oh, well, that's a mistake because on number 7 it asks for how many, not just the percentage. So really should have been 475. And the second part was 840. And then now notice that these numbers are going to be different because the answers that you see here were done by using those nice even percentages of 68, 95, 99.7, which are not 100% accurate, right? When you use Desmos to do it, you got better answers here. So you can see that every one of those is off by a little bit, but that's not a problem. Actually, these are the better numbers. Okay, so that is the end of that homework video.